Good day. I'm Engineer Reynaldo A. Flordeliza from the Philippines of RA Flordeliza Engineering Consultancy. Our tech talk today is regarding the seismic instrumentation with Midas Gen, response spectrum and linear time history analysis. The content of the subject deals with the brief of the Philippine earthquake. 2. How Midas support the seismic instrumentation installation. The guidelines on earthquake recording instrument posed by the DPWH, which is the Department of Public Works and Highways. 4th is a case study of retrofitting the St. Peter Memorial Chapel. 5th is the installation of accelerograph with precision, and the data interpretation based on the design earthquake, which was extracted from the instrument versus the site response. Structural detailed engineering verification, response spectrum analysis, and linear time history analysis. You can visit my website at www.rapconsult.org. And that is my office, RA Flordeliza Engineering Consultancy. Midas Gen support in our seismic instrumentation services, such as accelerograph installation, which from then we have data extraction used for structural health monitoring. 2 is the seismic accelerograph interpretation for comparing the design level and the site specific spectra. And the 3rd is the structural detailed engineering design for identifying the local and global retrofitting. However, there is an importance of the structural engineers in the aspect of earthquake monitoring devices for structural evaluation purposes for structure utilizing Midas Gen. But before I do that, in the Philippine setting, we have history how it all started. Well, there was a earthquake impact reduction study made for Metropolitan Manila here in the Philippines by these 3 agencies, namely the JICA, which is the Japan International Cooperation Agency, the Metropolitan Manila Development Authority, and the Philippine Institute of Volcanology and Seismology. That was way back 2004. Well, it's about an impending magnitude 7.2 earthquake, which they call it the big one. It is characterized by strong ground shaking, about 8 and 9 intensity, along most part of the metropolis, and a liquefaction area and landslide caused severe damage to buildings, mostly residential, thousands of deaths and injuries, disruption of lifelines and services, and widespread fires. Is it possible here in Metro Manila? Yes, definitely. When will it happen? We don't know. As far as the research is concerned, there is a repeating estimated about 200 to 400 years that this earthquake repeat by itself and transected in our West Valley Fault system, and we are about 350 years ago since then. So the time is already ripened. But however, how do we characterize the magnitude of 7.2? Well, it is similar to a 50 megaton bomb. So in Haiti, they have epicenter some 10 kilometers from Port-au-Prince. In the Philippines, they call it Scenario 8, which is in Metro Manila, according to BFOX. And the Philippine setting, the Philippine archipelago, has 2 plates that pushes the Philippines upward. And there is about 6 quake generators that are being monitored with different kind of magnitude, especially for the fronting the Manila Bay, about 7.8 is the magnitude. So, and then, what dangers await when the West Valley Fault moves? Of course, as estimated by the agency, the JICA, the MMDA, and the FEBOX, there's about 40% of the residential building will be damaged, about 38% for the 10 to 30 story buildings, 14% of the 30 to 60 story buildings are estimated. And there's a large percentage also for public buildings that includes the residential as well. Are we doing something in dealing with these percentage issues? Yes. Well, there was a guidelines that has been disseminated to all building engineers since November 28, 2007. And it has been repeatedly done 2011, and it says in the guidelines that includes earthquake. However, all buildings, especially those that have existed 15 years or more, shall be subjected to comprehensive evaluation. If this is not done, a certificate of structurability has to be in place. But however, if not done, the owner as well as the engineer on record have civil liabilities in case there is a collapse. Okay, let me clear on that. That was 2007. Therefore, it is imperative that buildings qualifying for 15 years and above have to be re-evaluated first before installing accelerograms. Why? Maybe they are really aging. Some of these buildings are no longer compliant with the present National Structure Code of the Philippines, and the mode of vibration has to be updated and checked to set a baseline. And if that is so, there is a need of strengthening. It has to be in place to have a structural integrity. And the design-based level parameters such as the response spectrum must be known. Angle of citation of which major weak direction of building must be identified. To determine the major of interest where accelerograph is to be oriented. Building storage drift limits has to be checked also. But in Midas, it supports now some data extraction and structural health monitoring. Let's take a look on the IRR that I have said. IRR is the implementing rules and regulation guidelines from the DPWH, and ERI is the earthquake recording instrument. So the DPWH IRR run this way. It is a guidelines and implementing rules and recording instrumentation for buildings. So it was already signed into law. However, in the guidelines, there are certain type of building for government building, but we will go to private building because we have so many buildings here in Metro Manila owned by private entities. And it says, building above 50 meters in height should have at least 3 accelerographs. Hospital with 50 beds should have 1 accelerograph. Commercial building with at least an occupancy of 1,000 persons or a gross floor area of 10,000 square meters will have 1 accelerograph. And industrial buildings such as plant with 1,000 persons and 10,000 square meters should have also 1 accelerograph. However, you need to set a baseline. What are needed in setting the baseline? According to this IRR in the paragraph 3 requirements. Buildings to be instrumented need some additional requisite information such as plans, These are as-built plans. These are the original plans because these are the birth certificate of the building. So you need also to have some reference like the architectural, including all the traverse line within the boundary of the property. So you have a reference point to coordinate when you put some reference to the in reference to your accelerograph. You also need some like this structural calculation that can be in interoperable model file, whether that's in ETAB, STAAD, or any software, standard software that can be referenced, and you can save it in this USB drive and any means of storing your data. However, if you have those data, you can also have some analysis in the dynamic mode shapes, force vibration tests of buildings, in the finite element dynamic analysis. So you can know what kind of vibration they have and period. You also need to know some drip limitation of the building if it has been okay. So drift pressure limit is about, from this kind of design, it's about 0.015, and we believe it's not being exceeded. Determining of dynamic characteristic of structural system is important in assessing their vulnerability and in developing procedure to analysis and design future structures. Data recorded from instrumented structures is used to determine the structural characteristic. Okay, so you also need some comprehensive soil tests and reports. So you need a boring log, something like this, to know the stratification of the soil. So we can reference the seismic waves from traveling from the fault line to the having a distance to your site. So boring can give you some geotechnical report on this. However, in the industry, they put a lot of typical accelerograph. Some put seismographs, some put accelerograph, but it's preferable to put accelerograph for buildings. Seismograph, let's give them for the in the earthquake recording, such as the authorities like the PHIVOX. So again, it detects acceleration of the ground. In the National Structural Code 2010, there's an excerpt, unless waived by the building official, every buildings in seismic zone 4, Philippines has high seismicity, with 50 meters a night shall be provided with not less than 3 approved recording accelerograph. It is specific. You should install accelerograph. Well, the code developer feels that the Philippines needs to have its own set of earthquake records in order to have a degree of confidence in the seismic parameters being used in the seismic load provision. It is used for structural evaluation. However, the main objective of this is for the seismic instrumentation program for structural system is to improve our understanding of the behavior and potential for damage of structure under the dynamic loads of earthquake. This will be achieved through the development of integrated network that measure the earthquake source, transmitted from ground motion, and the structural response. This measurement will be correlated with observation of structural performance to evaluate the current design and construction practices in order to minimize damage to building during future earthquakes. Let's now take a close look of a case study, and this is the building we have retrofitted before. This is a structural investigation of retrofitting of St. Peter Memorial Chapel. Well, I just want you to know that this building is somewhere in the Google map to show you where it is located. I'm using this technology so when you refer to a project you can easily know where it is located. So let Google Earth find its way to know where that site is. So it is in Quezon Avenue, it's right here in the Philippines. So I'm just making it a little bit zoom. So, and this little man, I put it there. So he'll show me how the building look like. There you go. The building is about 3 to 4 story at the front, but however it's a 6-story level at the back, and you have those structure billboard sign which we have included in the model. So the as-built and site info was done through a series of measurement of all the members. You can see there is a lot of colors, changing colors in the model because of different sizes, different strength, and the green one look like these are steel structures as I have shown you in the real picture. And we have modeled that from the works menu. We have already modeled on a wireframe indicating the red for concrete and blue for steel. And from the analysis, previous analysis we did, we have found out that the column condition based on the code, utilizing the present code, the National Structural Code of the Philippines, the demand capacity ratio of the columns are failing. So we have to introduce a lot of retrofitting solution by getting a global analysis by way of bracing. For the beams and columns, we put some jacketing, and that's the technique we did for this structure. So there is a really need for bracing so that the other columns will sustain the integrity. What we did in the structure is to brace all the perimeter columns, but we feel that it's not economical, so we remove all one at a time, and we come up that we need only these braces at this area to compensate the strength of all the columns, so it will not exceed the demand capacity ratio. So beams also were retrofitted because we found out the demand capacity ratio had been exceeded. Okay, this building is now retrofitted. Okay, so we use some proprietary program in retrofitting this because we use some carbon fiber, but however for steel we use the traditional method of steel design and retrofitting the braces. So now this building has been retrofitted and now ready for installing an accelerograph. But however, we are being guided on how to install seismic instrumentation with proper precision. Okay, instrumentation shall be installed with normal standard of professional care. The need for long-term reliability shall be foremost in the installation work plans in detail. There must be a due diligence from you engineers to find the what. Well, we have to find the center of mass and rigidity and equating this to the center of gravity of the building. So in theory, we have the overall mass and stiffness of the structure is always considered. So the center of rigidity may not coincide with the center of mass. So there will be a torsional effect when it comes to the interaction of the soil, when there's a rocking, twisting, jumping, swaying to the left and to the right. However, in the actual frame, in the theory, there is a reduction of multi-degree of freedom system into an equivalent single degree of freedom. So we discretize the frame as a mass, and that kind of joint is being discretized as a stiffness on every level. So a mass has been equated to a single degree of freedom, because we need only a shape to give us a drift, a value where the mass participation factor is always considered. So this is how in theoretical application, where the mass is simplified as single degree of freedom to get a displacement on each floor, considering mode 1, mode 2, and mode 3. In the dynamic equilibrium for earthquake, using a response from the accelerograph of the ground motion, displacement can be determined. If you have an acceleration from the response history of the accelerograph, that can be equated by the effective earthquake load, as simplified in this formula, and simplifying this utilizing the Midas concept. So you can import all the response from the accelerograph, the data, and putting that here, assuming we want to find at a certain time with a function of fluctuation of the accelerograph of that earthquake. In this case that is 0.3202. So multiplied by the gravity, which is 9.0806, you have equivalent of 141.3 kilonewton as expressed by the mass multiplied by the ground acceleration. Now, installing the instrument, there are certain guidelines we are to observe. But however, I will consider number 2, number 3, and number 5, because 1, 4, and 6 is just minimal for us to understand. But however, 2, 3, and 5 are most crucial to observe. First, we have to know the center of mass and rigidity. As we know, in buildings it may not coincide unless there is a very symmetrical arrangement, even the stiffness of the columns and the positioning of the core, as well as any enlargement of column is not present. In buildings, and it says again, sensor location accuracy. Within the structure, sensor location accuracy should be 10 mm or better in all 3 axes relative to the designated reference sensor. If this will be a reference sensor, your alignment must not exceed 10 mm to the x-axis, 10 mm to the y, and 10 mm to the z. But however, at the mid portion, first you have to simplify your model into a single degree of freedom wherein you can get the z-axis. This can be done by utilizing the center of gravity of the building. So in the final alignment, that should not be more than 10 millimeters. However, this is very difficult to lay out, but it is possible. You just have to use some total station and proper coordination at the site, so you will have that exact positioning. In the Universal Building Code, the alignment of the tree is suggested. However, with the different towers with a common podium, so the IRR says for clustered buildings with complete similar design and construction, it should follow the same requirement for single building. Meaning, if that is 50 meters and above, So you will be required at least 3 accelerographs. So this is why it is a must that engineers have to be very keen on how the device was properly located and installed. This is due for the correct data extraction to be interpreted for damage identification use, where the major axis of excitation angle of the seismic response to the building is our utmost interest. However, industry suppliers have so many diversified output data reports such as like this. You will be presented with different kind of hard copy like this, sometimes it's just a monitor output, sometimes you have a generalized output like this. So the structural engineers does not necessarily need that. So in the data extraction as per IRR, it says immediately after the occurrence of the magnitude 6 earthquake or greater, the building officials are required the owners to retrieve the data and to have the data interpreted by a certified civil structural engineers. The data interpretation shall be submitted by the owners to the DPWH for storage purposes, post-earthquake safety evaluation of the buildings, and emergency response demand to the concerned building officials. However, we really don't need a data coming from a thermal paper or a hard copy paper. It should always be in a numerical format data, accelerograph raw data output for the use in mathematical modeling of the building. This can be extracted and imported to the standard software used by structural engineers. However, data can be initially set up on a hard copy or something like this, but it should be readily available in a numerical data format. Okay. However, from that numerical data, you can easily plot your response spectra. So you have to have a base reference. In Midas, from the right, you have is a waveform coming from an accelerograph device, and based on the x-axis, and utilizing the raw data from a numerical output, we can easily import that into Midas. So you can have you will see you have a similar waveform on this aspect. Data import to Midas Gen is for site-specific hazard assessment. You can import your data, you can convert it into a response spectrum, and you can generate a design spectrum also. Midas support in our seismic instrumentation services, such as comparing the design and the site-specific spectra. How? So from here, this is a site-specific taken from the accelerograph, and we have found that the spectrum look like this. And comparing this to the design-based level of a UBC, because we normally use in the Philippines the UBC 97. So we have from the distance of a certain locality, the coefficient are considered. So spectral data is being plotted. So this is the format of the spectrum. So in an Excel file, you can do that the same. So from the left, the orange is the design spectrum of the building, and on the right is the spectrum created from an accelerograph. Plotting both them together, you will notice there is an exceedance on the base level. So now we go to the structural detail design. Structural evaluation process is just assessing the building structural health condition and detecting damage. First, you put your instrumentation. Then when there's an earthquake, you check your building utilizing the PIMA standard to mitigate. And then if you need a further analysis on the performance of the structure, then you have to use the accelerograph and check the performance from the base level. And if you have seen some failing member, that's the time you can retrofit and upgrade your building. With Midas, there are 3 levels of analysis of which you may be able to perform. What are those? Response spectrum analysis, pushover analysis, and time history analysis. But we will be taking up this response spectrum and time history analysis because pushover is not within this premise of discussion. From the analysis, you may know which quake direction are likely to damage the structural member that are getting to be busted. And so, the stability of the structure during earthquake event is characterized by the proper seismic parameters such as the effective ground acceleration values. Corollary to this, it is critical role of the material property, the detailing for ductility, and the design for redundancy and the safety of the structure. Structural health monitor is just something like this. You have an accelerograph reading the acceleration of the ground. Somebody has to interpret that and extract. And then before you do that, you have to know structural consultants to interpret that and analyze the building so he can tell you if it is okay or it will be needing retrofitting. Therefore, studying response record from the instrumented structure provide the means to identify the performance problem of the structure and therefore devise and select the best possible retrofit and upgrade. However, you have to know if the device was properly installed so you can correctly correlate this to your finite element. Again, in the IRR, there is a certain clause on the orientation of the instrument. All instruments should be installed with the same orientation relative to the building, with orientation chosen such that the reference or long dimension of the instrument aligned with the major axis of the building. There is an axis we are talking about. This is the excitation angle. Very important. This angle is the angle where you will have the maximum response of earthquake, where he will find your building of its weaker direction. In Midas, it has a picture that can perform and locate the major excitation angle of our interest. How? In this case, with the model we are talking about and the case study, and the plan view of the building, of course, we have found that in the general analysis to the finite element, we are given these coordinates. So that is calculated and positioned to that effect. So you know, counterclockwise is your direction from 0 to 90. So the relative axis, which will be the major interest, has been calculated to be 4 degrees from the analysis. That is the maximum response of the earthquake. It has been calculated at 4 degrees. So now you know that you can now position your accelerograph having a reference on the Y and X. So device orientation is about 4 degrees from the reference X. So again, sensor within a structure should be oriented in a logical manner in line with the structural primary axis, or as needed to measure the response quantity of interest. Sensor should be mounted within 0.5 degrees of the desired orientation within the structure. Sensor orientation is critical to the data interpretation and shall be well documented and controlled. So you can only have more than 4.5 and it cannot be less than 3.5 with that 0.5 degrees for your orientation. This is how you position your accelerograph. That will be now your reference for the north and the east and west. Once the earthquake busted you in this way, there will be an effect on the north and east-west direction of your building. So from the ambient vibration test, with that orientation, you can know immediately your values. And considering from the analysis, you can get all this frequency period based on the analysis. What if the building experienced now a new set of earthquake record in exceedance to the threshold of the baseline earthquake reference? This is all applicable to all structure, whether it has been designed using a code-based design level analysis, response spectrum analysis, or we call the performance-based pushover analysis. Let's take a look on a raw data file coming from an accelerograph. In this case, we took an axis of X. So the source is a kind of accelerograph we call SysCom. And from here, we plotted the response spectrum of the code base, and from this raw data we plotted it from Midas. It ran this way. But however, take note, the fluctuation of the response spectrum start with a greater number. This point about 0.8 something, and the response spectrum for the design UBC 97 start with 0.4. So the peak is quite high, and the sinusoidal peak is really greater than the design base level. So again, comparing these two, we have found out that fluctuation is too big, and you have the issue to investigate your structure because it exceeded the base level spectra. Now what? It is imperative to interpret area and monitor the status of the building and proceed evaluation process. You have to check the model input again, then update and modify, incorporating the retrofit properties. Check the allowables, drift, demand, capacity ratio, etc. Response spectrum analysis and check failed members. Apply time history analysis and check failed members. Select best possible retrofitting solution to the system. And update when need to strengthen the condition of the structure. How do we do that in Midas then? The approach is this way, updating. First, because these are retrofitting using carbon fiber in the original section, you have to take note on the section stiffness and scale factor of all the members you have retrofitted, including columns, beams, or slabs, because you have to incorporate those. From here, I have here an Excel file that I have made with a concrete section properties and a composite properties using a carbon fiber. All component of the carbon fiber utilizing its strength is already programmed here, including the moment of inertia as well. So from the right, what I did is just to get the section properties of each member in inches. However, on the left, I use metric because I'm used to English system. You will notice there's already numbers there in orange that has been updated already. This is how we do it in Midas. So if this is the section having that carbon fiber stiffness, so we have to calculate the overall stiffness scale factor. Now this is how we did it in the basics. Of course, I have a file, and then we are concerned of the modification. Let's say we don't know that. So having a number there, I just copy it there, and voila, I have all this area, moment of inertia, and the scale factor of the weight. All I have to do is to place it here. So that's how we did the updating of the members. Okay, from here we all copy this and paste and update to the Midas. Okay, so that's how we did it in Midas Gen. Okay, response spectrum analysis. So in the response spectrum analysis, we get the accelerograph data and extract it, and we convert that to a site-specific response spectra. Then that's the time we analyze it using a response spectrum analysis. There are procedures for response spectrum. One is you have to know your response spectrum function and your response spectrum load cases. Okay, and you have to set the response load case, and then you run the analysis. From this analysis, based on the actual accelerograph recorded converted response spectra, you can now see whether the members have been severely busted. Okay, I show you from here. This is the data coming from an accelerograph. Okay, I did is to copy this, all of which. Okay, then I copy all of those, and then I just have some analysis here. Dynamic load, okay, static load, but you have to use dynamic load and put that response spectrum. I delete that, then I'll just add a new response spectrum. What I have copied before is I paste it here. So then I plot, I have a response spectrum. Okay, now we go now to response spectrum load case. Now you have to assign a response spectrum at X, but however you have to know the major excitation if this will change. Scale factor for R is just the inverse of the importance over RW. You get 0.167. So adding that load case, you have a response at X. Similarly, for Y, it's just the orthogonal 90 degrees positioning of the excitation. So you just have to add this to the windows, and then you have this Y. So you have updated your major X and Y. Okay, let's close that, and you have this model ready. So we run the analysis, and from here okay, so result from here we found out that the demand capacity ratio has been exceeded. See, before it was retrofitted, all of which are okay, but now having an accelerograph data and putting a new response spectrum reveals that this demand capacity ratio has been exceeded. Now for the time history analysis, it is similar. From the extracted accelerograph data, we convert that to site-specific run spectra analyzed with time history analysis. But however, you have three procedural steps for linear time history analysis. You have to set the load cases, dynamic load cases, and time history function, and set the ground acceleration. In Midas, there is a clause stating the function on the X. This is from a raw data file, and you have to be keen on the angle of excitation of that angle, which is based on the reference of X. Okay, so from here, first we did is to get the dynamic load, then time history, and ground motion. We will not discuss this too much of these three because we will not be talking about this in the later time. So we have to set a group damping. Group damping, because we have two kinds of material. You have the concrete and the steel. So you have to set the damping of each one, where we know the damping of the concrete is about 5%, 0.05, and for steel we use 2%. So once that have been assigned, you have to use strain energy proportion so that there will be a distribution of the strain energy on each material. Now, getting a load combination on the load case on the time history, you have to modify that, and you have to use some technique on the changing these values. You need a linear, a model, and a transient, because it is a transient. On the time end, I use 34 seconds because this is the time of, recorded by the accelerograph. You will notice here from 00 we have gone to the extent of copying the time only for about 36 seconds. Okay, so that's how we do it. Now, having assigned those time history function, from the analysis, running the analysis, we can have these values, and it was found out with Midas it is easily completed in 101 second time. So that's very, very fast. And we found out, using the time history analysis, before these beams were not failing. Now it readily shows that there are more beams failing using time history analysis. Therefore, it has an accurate way of predicting damage when it comes to retrofitting system. But how to set a building simulation with time history analysis? Is this simple? You just go to the Result tab, that's your first procedure, and you will be prompted by a time history result, that's your second. And the third is to set an increment where you feel it will be more faster. In this case, it is 0.001. I changed this to 0.05 to elevate the speed. You can assign 0.05, 0.09 if you want. So this is a simulation of a linear time history of the model we did, including the analysis, where we set the instrumentation citation angle at 4 degrees, having an orthogonal 94 degrees in the y direction, which has a peak here. Is a simulation of a linear time history analysis of the model. Now we can note that the time steps now moving, and in a while that vibration can be detected by the building itself. having a 1.03 peak ground acceleration for a 36-second period. You will note that this earthquake is too strong, that the vibration around the behavior of the structure is tremendously swaying, which is not acceptable. And from this analysis, we have found out with this kind of peak ground acceleration, the total building was really damaged and collapsed, maybe. And that is not what we really intend as an engineer to check the behavior. Well, in conclusion, the importance of building instrumentation, recording the acceleration response of the structure have served the scientific and engineering community well and have been useful assessing in both new and old design analysis procedure, improving code provision, and in correlating the frame system response with damage. Accelerograph provides a very useful tool in today's earthquake engineering. The benefits with Midas Gen are it is capable of handling any project type I work with. Easy importation of accelerograph data to the copy and paste. Automatic checking of storage rip ratio in accordance with the code. Easy to extract output of center of mass and center of rigidity for each floor and the whole structure for the center of gravity. Automatic calculation of major and orthogonal angles for seismic loading and seismic instrument installation. Easy handling of multi-tower structure with independent vibration. Quick definition of site-specific response spectrum and time history function for site-specific seismic hazard assessment. Support all the major analysis type, equivalent, static, response spectrum, pushover, we'll call it performance base, and time history, required for site-specific seismic hazard assessment. Support all the global retrofitting techniques like revision of geometry and stiffness, addition of dampers and base isolators. It's a one-stop solution for site-specific seismic hazard assessment. Well, this is my office and this is my card, and these are my services. I